Hello everyone, my name is Aditya Tiwari, Assistant Professor CSVTU Bhilai. In this tutorial we cover trees. So trees, it is a non-linear type of data structure compared to array, linked list, stack and queue. These all are the example of the linear type of data structure. So move on the non-linear type of data structure. Why we go for the non-linear type of data structure? Because when we working about the corpus amount of the data, or we can say big amount of the data, at that time when we go for the operation like a searching part, insertion part, deletion part, and we use a linear type of data structure, it is quite taking some lot of time to operate them. We can go for the another type of data structure, that is called a non-linear type of data structure. So we can easily perform all the data structure operation in less time. So tree is a hierarchical data structure which stores the information naturally in the form of hierarchical style, or we can store our data in a non-sequentially way. In a linear type of data structure, we should to store our data in a sequentially structured way. Trees is one of the most powerful and advanced data structure. It represents the nodes connected by the edges. By this graph, you can understand the non-linear type of data structure tree. So here we having a root node, that is A. Without root node, you can't make a tree. Root node is a mandatory of any tree. Tree having like this one, A produces childrens like B and C. Both B and C are in the same level, and B and C are the siblings of A. You can produce more than 2 children also in the tree. That is depend on the restriction of tree. If we are working on binary tree, the restriction is that you can produce maximum 2 children or less minimum 0 children. But you are talking about the M-way tree, B tree, all kind of a tree producing, it's depend on the order of M can produce the child. Right now we can understand only the child's and tree parents and grandparent concept. Here B and C both are the current successor, or we can say both are the current child of A. A here is a root node, B is a left successor of A, and C is a right successor of A, and B and C both are the siblings of A, and both are connected by the edges. Again B produces 3 children like here D, E and F. D, E, F all are the successor of B, and D, E, F are the nodes, are the grandchild of the node A also. Here the B, D, E, F and H are the subtree of left subtree of A, where the C and G are the right subtree of A. Here B is a left children of A, but B is also a parent of D, E and F also, and B also a grandparent of H also, because H is produced by the E. E is a parent node of H, E as well as the child node of B. So we can say H is a grandchild of B, or vice versa we can say B is a grandparent of H. So child nodes are D, E, F, but D do not producing any child, that is why that is called a leaf node. F is also not producing any child, that is called a leaf node, but E is an internal node because E is producing H child. In the same parallelly way, at the right hand side of A, C is a right child of A, and C also a parent of G also. So we can say G is a grandchild of A, or we can say A is a grandparent of G. So this is a hierarchical tree structure. Tree is a collection of elements called nodes, where each node can be arbitrary number of children. One thing you can understand, which node is producing a child, that is called a internal node, and rest those nodes are not producing any child, that is called a leaf node. In this figure, D, F, H, G are leaf nodes. B and C are the siblings. Each node excluding a root is connected by the direct edge from exactly one other node, parent to children. So, one by one you can I will describe you all the fields like root. Root is a special node in a tree. The entire tree is referenced through it. It does not have a parent. Second one is parent node. Parent node is a immediate predecessor of a node. Next one is a child node. All immediate successors of a node are its children. Siblings, nodes with the same parent are called sibling. It means siblings nodes are all at the same level and the same position of the parent node. Next one is path. Path is the number of successive edges from source node to the destination node. Suppose when you travel from root node to the grandchild node, it means you follow the two edges, and that two edges, combination of two edges is called the path of that particular destination. So, source to destination will be covered by the path, not by the edge. If we are using a single edge, that is called the edge, but combination of two edges is called the path. Height of the node. Height of the node represent the number of edges on the longest path between the nodes and the leaf node. As I told you, leaf node means do not producing any child. Next field is height of the tree. Height of the tree represents the height of its node, its root node in the tree. Next field is depth of a node. Depth of a node represents the number of edges from the tree's root node to the node. Later on I will describe you, explain you one by one what is by the example, by the diagram, how depth of the node, how the height of the node in the tree. Next field is degree of a node. Degree of a node represent a number of children of a node, that is called a degree of node. Next field is edge. Edge is a connection between one node to the another node, or we can say one vertices to the another vertices. It is a line between two nodes or a node and a leaf. So, one way you can understand the concept of level of nodes or height of the nodes. Here discuss about the level of nodes. Level of a node represent the number of connection between the node and the root. It represent generation of a node. If the root node is at level 0, its next node is at level 1, its grandchild is at level 2, and so on. We can understand by this diagram, like here in a level 0 having a single node, that is called a root node, and inside the root node we having a item is A. Root node in a single tree we having only a single root node. We can't produce more than one root node. So, A is a root node. A produces two children like here B and C. B and C both are the siblings and both are the current child node of A. That is why B and C holding the position of level 1. Again B producing a child's D, E, F, and C also producing the G. D, E, F and G are the grandchild of the A, but having different parent node. D, E, F the children of B and G is the children of C, but all D, E, F and G are the grandchild of the node A. That is why D, E, F, G are situated at the level number 2. Next one is E also producing a child H, and H is a successor of E. That is why it holds the position at the level 3. So, H is a grandchild of node A. So, here in the tree level 0 having a single item, that is called A, level 1 having a two items B and C, level 2 having a 4, D, E, F and G, and level 3 having a single item, that is called a H, that is called a level of tree. So, to be noted that if a node has no children, it is called leaves, or we can say extra node. It means if any node don't produce any child, that node is called a leaf nodes, or we can say that is called a external node. Nodes which are not leaves are called the internal nodes. Internal nodes have at least one child minimum. A tree can be empty with no nodes, or a tree consists of one node called the root node. Move on the next one, the height of the node. As we studied, height of a node is a number of edges on the longest path between the node and the leaf, between the root node and the leaf node. Each of the node has height. In this figure, we can understand A, B, C, G can have height. Leaf cannot have height, as there will be no path starting from a leaf. Node A's height is the number of edges of the path to K, not to D, and its height is 3. Noted that height of a node defines the longest path from the node, it means from the root node or any node to a leaf node. Path can only be downwards only. By this graph you can understand, if we are talking about A, height of the A is, we can find out the longest path. If we traverse left hand side, the current successor is B. Again B having a successors are D, E and F. If we count the left hand side, the maximum height is only 2, because either D, E, F having a 3 nodes, but all are in the same level, or we can say all are the siblings of that B, all are the siblings in the same level. So, the height of the at the left hand side is maximum height is only 2, but if you travel at the right hand side, A to C, C to G and G and H are also the siblings, but G also produces another children's K and L. It means K and L are the siblings, and K and L situated at the height of 3. That is why we can say the maximum height of the A is 3, not a 1 or 2. If you traverse at the left hand side, the height maximum is 2, but you traverse at the right hand side of A, the height maximum is 3, that is why we take a 3. If we talk on another node, that is called a C, C also producing 2 children G and H, but if you traverse at the right hand side, the only having a single edge, that is called a H, and the left hand side you having 2 edges like C to G, G to K, either G to L, but K, L and L both are the siblings. So, maximum height of the C is 2, or the height of B is only a 1. In this way, we can find out the height of each and every node, or especially internal nodes only, not external nodes. Next is depth of the node. While talking about the height, it locates a node at bottom where for depth. It is located at the top, which is root level, and therefore we call it depth of a node. In the figure, you can easily understand node G's depth is 2. In depth of a node, we just count how many edges between the targeting node and the root node, and ignoring the direction node, depth of the root node is 0. So, depth of the node, if we are talking about any node like G, G having a depth is 2. Why? D is a successor of C and C is a successor of A, and A is a root node, which is having a depth is 0. That is why the depth of the G is 0, depth of the G is 2, depth of the C is 1, depth of the B is 1. Like that, we can easily understand the depth of any node. So, the advantages of tree. Tree reflects structural relationship in the data. It is used to represent hierarchies. It provides an efficient insertion and searching operations. Trees are flexible. It allows to move subtree around with minimum effort. So, now the next is binary tree. Binary tree is a kind of a tree. Binary tree is a special type of data structure. In binary tree, every node can have a maximum of 2 children. This is a restrictions part inside the tree, which are known as left child and right child. One is left child and another is a right child. It is a method of placing and locating the records in the database, especially when all the data is known to be in random access memory. We can say RAM. So, the definition of binary tree is a tree in which every node can have maximum of 2 children is called as binary tree. Minimum is 0, but you can put the maximum of 2 children. The tree represents binary tree in which node A has 2 children like here B and C. Each children have one child, namely D and E. So, he can understand A is a root node, A having a 2 children B and C, B also again producing a D, C is also producing a E and E again having a child G and H. Here A is a root node, B and C, B, C and E are the internal nodes, D, G and F are the external node, or we can say the leaf node. So, types of the tree. Binary tree can be of the following types like full binary tree. A binary tree is full binary if every node has 2 or 0 children. There is only connected a single child, that is not possibility inside the full binary tree, either a 0 children, either a 2 children in the full binary tree. Following are the example of the full binary tree, means we can also say a full binary tree is a binary tree in which all nodes except leaf have 2 children, like 18 is a root node, 18 having a 2 childs 15 and 20. Again 15 having a 2 childs 40 and 50. 40 again having a 2 childs 30 and 50. If you here see 18, 15, 40 all are the internal nodes and all are producing a 2 children. If you are talking about the 20 can't produce any childs, that is called the external nodes, or we can say leaf nodes. 50, 30 all are the leaf nodes. So, every node having either 0 children or either a 2 children, that is a full binary tree. In a full binary tree, number of leaf nodes is number of internal nodes plus 1, like we can write the expression is L equal to I plus 1, where L number of leaf nodes and I is the number of internal nodes. Next is a complete binary tree. A binary tree is complete binary tree if all levels are completely filled except possibly the last level, and the last level has all keys as left as possible. By this diagram, by this following example, we can understand the concept of complete binary tree. Here the root node is 18, 18 produces 15 and 30, one is connected at the left hand side, one is connected at the right hand side. Again 15 produces again 2 children 40, 50, 30 again produces 100 and 40. The one by one generation we can fill. Again we start 40 will be connected by the left 8, then 40 connected by the right hand child 7. Now next is new element is 9. 9 is should be connected by the left hand of the 50. Suppose again I want to connect some item like 100. The 100 is a bigger item of all that one, but 100 should connected by the right child of the 50. We can't connect or any other end. So we have to fulfill the left space first, then we move on the right space. That's the concept of complete binary tree. Next is perfect binary tree. A binary tree is perfect binary tree in which all internal nodes have two children and all leaves are at the same level. Following the example like that, 18 produces 15 and 30, again 15 produces 40, 50, 30 produces 100 and 40. All leaf nodes are in the same level. It means 40, 50, 100 and again 40 are fixed at the same level. That is called a perfect binary tree. A perfect binary tree of height h, where height is the number of nodes on the path from the root to leaf, has 2 to the power h minus 1 node. Here the example of a perfect binary tree is: ancestor in the family keep a person at root, parents as child, parents or parents as their children. Next one is a degenerate tree, a tree where every internal node has one child. Such trees are perform wise same as a linked list. Like here we can by the example, 10 produces only single child, that is a 20, that is a left successor. Right again producing a single child, that is called a 30, but is a right successor. Again 30 produces a single child, 40, that is a right successor. Its type is tree is like a linked list. So this is a again kind of tree. This is a degenerated tree. Last one is balanced binary tree. A tree is balanced if the height of the tree is O inside the bracket O of log n, where n is the number of nodes. So now we move on. The next topic is binary tree traversal. Binary tree traversing is the process of accessing every node of the tree and exactly once. A tree is defined in a recursive manner. Binary tree traversal also defined recursively. There are three techniques of traversal. The first one is pre-order traversal, next one is post-order traversal, and the last one is in-order traversal. In a pre-order traversal, first you fetch the root item, then you fetch the left items, left subtrees, then you fetch the right items. In a post-order traversal, first you fetch the left one, then right one, then in the last the root one. In a in-order traversal, first you fetch the left one, then root one, then right one. One by one we can understand by the an example, we can deliver you by the example. So first one is pre-order traversal. So the algorithm of pre-order traversal is step number 1, start from the root. First you have to fetch the root item, then you move on the another step. The step 1 is first you read the root item, that is called a inside the pre-order traversal. Then go to the step number 2, then go to the left subtree of the root node, then step number 3, then go to the right subtree of the root node. In a step 2, you cover all the left hand items of the A. Well, once you cover all the left items, then you shift to the pointer to the right hand side of the root node A. Like by this example we can understand, here we having a tree, A is a root node, A having a two children B and C, B is a left successor and C is a right successor. Again B producing a single child, that is a right successor, that is called a D. D again producing E and F. A producing at the right hand side is a C and C producing a left hand child a G and the right child is H. So one by one we can understand how we go for the pre-order traversal. As I told you in the algorithm, first we go for the root node. So we divide this tree into 3 parts. First one is a root node. Here we having a root node is A. Left subtree items are B, D, E and F. B is a current left successor of A, that is why the left subtree of the A. B having in the same position, D is connected the right subtree of B, E is connected to the left subtree of D and F connected to the right subtree of D. So, after reading the A, then we go for the left subtree, we fetch all the elements, the same phenomenon. When we traverse on the, when we shift the pointer at the left subtree, first we point, well, first we fetch read B, then we check left child, here we do not have any child of B, then we move to the right child of D. Before the reading of D, again I cross check the left child of D. If it is there, so first we go for the left child, like E, first we read D, then we go for the E, then we go for the F. Then right child, right subtree of A, that is a C, so first we read C, then we find out the left child, that is G, and then move on the right child of C is, that is called a H. So, first we read root node, then we cover all the items of the left subtree and we cover all the items of the right subtree, that is ordered pre-ordered traversal. So, by the pre-ordered traversal we having the sequence in this format. Sequence is A, that is a root node, then B is a left subtree root node, then D is a right successor of B, that is why D is coming. Now, next one is E, next one is F, then when we cover all the left subtree, then move on the right subtree. The first item is a root node is C, then we move on the left subtree is a G, and G having no child, then we go for the right child of C, that is called a H. The sequence is A, B, D, E, F, C, G, H. Next traversal algorithm is post order traversal. The steps are starting from the left subtree of the root node, then we go for the right subtree of the root node, and the last we go for the root node. Until we cover the leaf node, we can't move to the right subtree or the root node. When we first we cover the left subtree, all the nodes, internal nodes, leaf node, then we shift to the right subtree, then we cover the right subtree, then we shift to the root node. By this example, we can understand here A is a root node, B and C are the B is a left successor and the C is a right successor of A respectively. And again the same tree D is a right successor of B, E and F are the left and right successor of D respectively, G and H are the successor of C, left and right successor of C respectively. So, if we break this tree by this in a post order traversal, so first we cover the left subtree. The left subtree is that B, D, E and F. So, first we cover all the items of left subtree, like in that way first we cover in a post order, as I told you, post order is a left, right and root. So, first before we reading B, we have to check the left subtree of B. If there is no child, then move on the right child, that is a D. Before we reading the D, we have to cross check the left item is available or not. Here the left item is available. So, we shift our pointer to E. Before reading the E, again we cross check the E having elements or not. E is a leaf node, so we read the E and write also. Then we shift our pointer to the right child of D. Again we shift to F and again we cross check we F having a child or not. F do not produce any child, is a leaf node, then we write a F. Then shift to the root node. After covering E and F, then we shift to the D. D again we write the B. So, sequence of the left subtree is E, F, D and B. Then we move on the right subtree. Right subtree, the structure is C producing G and H. G and H are the left and the right subtree of C. First we shift the pointer at C location, we cross check the children is available. So, we have shift our pointer to the G. Again we before you writing the G, again we cross check the children of G, but here the G is a leaf node, that is why we write G after the B. Already we write the sequence of left subtree E, F, D, B, then we write a G. Now, again we cross check the right child of the C, yes, here is it. Now, we shift the pointer at H location. Before the writing of H, again we cross check the children of H, but here H is a leaf node, then we write the H after the G. Then we shift our pointer to the root node of C, then we write the C. So, then we shift our pointer at the root node, that is called A. So, already we write the sequence is E, F, D, B, G, H, C, and the last one is a root node, that is called A. Then we write a item of root node, that is called A, at the last position of this sequence of post order traversal. Next is last one is in order traversal. In order traversal starting from the left subtree, then we visit the root node, then we go for the right subtree. By this example we can understand. Say the same example, A is a root node, B and C again the left and right subtree of the A, and all of the elements are connected with them. So, first we disconnect the left subtree as per the in order. We can say first we cover the left subtree, that is the left subtree is B, D, E and F. Then we go for the root, then we go for the right subtree. So, first we divide the subtree, left subtree, that is called a B, D, E and F. So, we fix our pointer at B and we cross check in order left child is available or not. B does not have any left child, that is why we write the B, that is a root node, and we shift our pointer to D. Before the writing of D, again we cross check D having a left successor or not. Here is it left successor, so we shift our pointer to E. Again before writing the E, we cross check the E is a leaf node or not. Here E is a leaf node, so we write E. Then we shift our pointer to parent node, that is called a D. Now we write D and shift our pointer to F. Again we cross check F is a leaf node or not. F is a leaf node, so we write F. So, the sequence of left subtree is B, E, D, F. Then we shift our pointer to root node A, then we write the A, because root having only single atom, that is simply write the A after the sequence of that one. So, A we have to put the A at the right hand side of H. Then we shift our pointer to right subtree of A, that is called a C. Before the writing C, we have to cross check the left subtree. Here C having a left child G, we shift our pointer G, and again we check G is a leaf node or not. Here G is a leaf node, so after the A we can write the G. Again we cross check G having a right child, no, G is not child, G is a leaf node. So again we by the backtracking we shift our pointer to C. C is a parent node of G and H, that is why we write the C first and shift our pointer to the H. H is the right successor of C. Before the writing of C, we cross check having a left child or not. Here H do not have any left child, so we write H first. Then we find out the right subtree of H. Here is no any subtree or right subtree of H. That is why we end our operation. The sequence of this tree is B, E, D, F, A, G, C, and last one is the H. This is the in order traversal. So, this is the end of this today's tutorial. Thank you.